Okay, so we'll be talking next 3 weeks. Oh my gosh, that's too much. We'll be talking about physical oceanography. First part will be dedicated to the phenomenology, to learn what are the main problems of the physical oceanography. What physical oceanography does from the point of view of the problems, and the second part will be dedicated to the measurement type, to how do we measure, how do we do measurements in the physical oceanography. We have I have a suggested textbook, not because it's the best, but because it is available at the on the web. You can take it, and I will link to you. By the way, I will link to you this this PowerPoint so that you can copy it, whatever you need. And this is not so bad. But I know better than this one, but since you can use this from there, I will try to follow a little bit what it says there, and so I suggest you to follow what it says there. If you want to expand what you need, then you can go ahead and you can ask me. I'll give you some suggestions for the reading material. Topics what we are going to talk about is the part introduction. We will be talking about the historical and physical settings, a little bit about the history of the physical oceanography, which is to a certain extent interesting. Then we'll be talking about the atmospheric influence, because obviously whatever is happening in the ocean is depending on the atmospheric forcing, and vice versa, obviously. Then we'll be talking about the oceanic heat budget. So that means what are the sources and sinks of the heat in the ocean, because this is important. Then you will see later for driving the motion of the ocean. Then we'll be talking about the water budget, because there's both heat and water budget has to be zero, in theory, on a long time scale, because the ocean cannot lose or gain the heat, or cannot lose or gain the water, otherwise we'll have the lowering or increasing the sea level. The sea level, obviously there is some increase of the sea level, but we will be talking about this later when we are going to talk a little bit about the climate change. Then we'll be talking about the temperature, salinity, and density, which are the state variables of the ocean. Spatial distribution of over the world ocean of these state variables, which is another important issue, because it determines the motions in the ocean, because the motions in the ocean try to smooth down the difference between different parts of the ocean as far as the state variables are concerned. Then we will go and try to see how we can explain these the motions, explain in terms of the equations of motion with and without friction. Steady and time-dependent motions. So obviously there are motions which are time-dependent and which are steady and different parts of the equation describe different types of the motions. Then we will talk about geostrophic currents, which is a specific type of motion in the ocean. Wind-driven circulation, because this is one of the very important aspects of interaction, air-sea interaction. Vorticity in the ocean is a specific feature, specific characteristic of the ocean, which we use as in explaining and describing the vorticity. We will talk a little bit about deep circulation, about oceanic and planetary waves. So these are wave-like motions, which are obtained from the equations of motion in the specific assumptions. Then we'll talk about coastal processes, tides, seiches, and tsunamis a little bit. Coastal processes, because the coastal processes are different than the open sea processes. Open sea processes do not feel the boundaries, while the coastal processes are largely determined by the boundaries, by the coast. Then we'll give a few examples, like a Venice Lagoon example, which is very nice to learn some global processes. I'm not sure I can get everything here. Maybe, okay. And then finally, we'll pass to the methodology of measurements. All these things. So how do we measure temperature, salinity, and density? How do we measure currents? How do we measure the wind, and so forth? In order to, and we will learn some modern technologies or measurements which enables us to have the very nice and good spatial and temporal resolution, which is very important for studying some of these processes. Okay, so now we go to the introduction. The basis of our understanding of physics in the ocean is, first of all, our physical properties of seawater. Physical properties of seawater are, as I told you, state variables, which determine physical properties. Then we should somehow determine what are the important thermodynamic and dynamic processes influencing the ocean. What equations describe the processes, how they were derived, what approximations were used in the derivation, and do these equations have successful and useful solutions? Obviously, not obvious. It's the complete set of the equations do not have the analytical solution, but what we do a number of approximations and get some important solutions, which then, in a certain level of approximation, well describes what is happening in the ocean. And this is the point F. How well these some solutions describe the process, because since we, in order to get the solution, we do some certain number of assumptions, which then means that the analytical solutions do not describe perfectly what is happening in the nature, and so we have to know how well these solutions describe the real process. Which processes are poorly understood, which are well understood, so obviously there are different grades of understanding processes. Sources of information about physical variables. This is the second part of our course. What instruments are used for measuring each variables? What are their accuracy and limitations? What historical data exist? And what platforms are used, which the platforms are then important in offering different spatial and temporal scales. If you talk about satellites, ships, drifters, and moorings, satellites certainly have a much better spatial coverage, because they are doing their rotation on the order of a day, so they guarantee a very good coverage on one hand. On the other hand, they don't go deep into the ocean, they just cover the surface. So that's why we use, for example, ships, which can go with their sensors in the deep of the ocean, but they don't, on the other hand, they don't guarantee very good coverage and high resolution of the coverage of the ocean. So these are further details of our course. Then, what processes are important? Then we have a heat storage and transport in the ocean. Heat storage is to what extent and how the ocean, the gain heat stores in it. This is one thing. And then, obviously, ocean. If you think that the amount of heat which comes to the ocean at the equator is not the same as in the polar areas, that means that that we do have differences in the heat coming from the sun, and in order to smooth down these differences, we do have to have the transport of the heat in the ocean. So transporting the heat in the ocean is extremely important in trying to smooth down these differences between, for example, polar and equatorial areas due to the different heating of the area. Then we have the exchange of heat with the atmosphere and the role of the ocean in climate. Ocean and atmosphere, they exchange heat because they are in direct contact. And ocean plays an important role in the climate of the earth. You know that a simple example is if you live close to the sea, the climate is different than if you live in the continent. On the continent is something which is called, you meteorologists, you know, it's a continental climate. Continental climate means large amplitude between summer and winter, large amplitude day and night, simply because there is no, the ocean is far away, and then it doesn't smooth these differences between extremes. So the influence of the ocean, for example, this simple example is essential in determining the climate. You will see later on that the ocean determines also the climate change. And then we have a wind, and another way another type of influence of the atmosphere to the ocean, where we have the transfer of the mechanical forcing between the atmosphere and ocean due to the friction at the surface. The ocean, the atmosphere, the wind transfers the momentum into the ocean surface and moves create the currents. And then obviously ocean then influence the wind influences also the vertical mixing. So you have the formation of the surface mixed layer. So even though the ocean is heated by the sun in very thin surface layer, due to the wind mixing, the heat which is absorbed in a very thin surface layer is vertically mixed in a much deeper layers. Then we have the wind-driven circulation, which means on the scale of the ocean we have the wind-driven circulation, including the Ekman circulation, Ekman pumping of the deeper circulation and upwelling. This we will be talking a lot about the Ekman solution and Ekman pumping, which essentially describes, in terms of the equations and in terms of the phenomenology, it describes the influence of the wind on the currents in the ocean. Okay, so this is the historical settings. I will not, obviously this is too many data, but they are not essential for our course, but it's just to give you an idea that the first contact between science and the ocean starts in the 17th century, and you can see that how it really started with looking at the movement of the ships and drifting of the ships due to the currents in the ocean, which were not direct measurements, but they are simply looking at the drifts of the ship navigating in the ocean, and they reconstruct, for example, the currents. The first organized measurements was in 19th century, and this is the systematic study of the biology, chemistry, and physics of the ocean of the world, where there was already some instruments which enables people to do the measurements of the temperature, salinity, and state variables. And at the end of 19th century, the first direct current measurements have been done in a Florida current. Florida current makes part of this Gulf Stream system. Why there? Because there the current is very strong. So therefore, the first direct observation of this very strong current have been done there. Number of studies in oceanography started very early in 18th century, which means the studies of tides, because the people see very, very easily tides, because as if you live next to the sea, you see the tides every day in your everyday life, and you see that there are periodic measurements of the sea level. Okay, this is a this is continuous evolution history. Just I would like to give you an idea that in 1978, NASA launches the first oceanographic satellite, CSAT, and this project developed techniques used by generations of remote sensing satellites. So the first measurements of the first satellite remote sensing measurements started in 1978. So we have already like 40 years of satellite data measurements, which is a pretty long time series. First measurements have been done of the measurements of the temperature, sea surface temperature. Later on, there are a number of parameters which we are now able to measure, like sea level, like chlorophyll, that means the color of the ocean and so forth. But the first measurements, which are these here, are dedicated to the measurements of the sea surface temperature. We'll see later why so, and so forth. In 1993, the last point again, it's another interesting milestone of the oceanographic measurements, remote oceanographic measurements, is 1993. The topics Poseidon science team members published first accurate global maps of tides, which is based on the first satellite sea level measurements, which started in 1992. So in 1992 we have, from 1992 up to today, we have the first, we have the time series of the sea surface measurements of sea level measurements over the world ocean. The precision of these measurements is on the order of a centimeter. So can you imagine this? You will see later what is the coverage of the world ocean with these measurements, and how important are these measurements in reconstructing the evolution of the sea level. You know that the sea level, you probably have heard that the sea level is one of the important parameters which describe the sea level change or the consequence of the sea level change in the world ocean. So measuring with a high precision and with high resolution sea level of the world ocean is essential to understand how fast and how important are the climate change consequences over the world ocean. Okay, I'll skip over this evolution of some theoretical ideas. Yeah. Well. Okay, so now let's go again to historical settings. Historical setting from the point of view of the experimental approach. Experimental approach is this is the first direct organized systematic measurements of the oceanography Do you want me to open? No.
No.
No, because I don't want to go. I get to go. Yeah, the only one. Go ahead, and you too. No, you don't want. Okay. These are the first, the example of from the era of deep sea exploration. This is the first expedition organized over the world ocean, systematic measurements, which was like a 5-year long. And you see this line is how the ship was navigating and doing the measurements. And you see how, and it took five years to do these measurements. So in 5 years, the ship, the oceanographic ship, did the measurements not only at the surface, but did the vertical profile of the temperature and salinity. But you can see how relatively poor is the coverage of the world ocean. The only assumption you can do for this is that you assume that these measurements are synoptic. So that means that the measurements are, even though they did the measurements over the 5 years, the changes in these 5 years are so slow that this represents the picture of the world ocean in its one single moment, which is rather strong assumption. If you go ahead, you see, for example, the next step in the evolution of the oceanographic measurements, ship oceanographic measurements. This is for example, the measurements of research vessel Meteor, of German Meteor expedition. And you can see, and this was from 25 to 27, 1925, 1927. And it's dedicated, as it's obvious, to the southern Atlantic. And these dots are the stations, measurement station. And here, in 3 years, this is the coverage. So again, rather strong assumption has to be done in order to, assuming that these are the instantaneous measurements, that we have the instantaneous coverage of the entire southern Atlantic. This is this 3-year measurements. We call it synoptic. Synoptic means that at the same time, the instantaneous picture of the world ocean. This is another example of the newer studies over the northern Atlantic, and done by Woods Hole Oceanographic Institute, which is American Oceanographic Institute. And you can see that here, as the map of station is the map of the coverage is much more detailed. And obviously, what you can see is that this is dedicated to the study of the Gulf Stream system, which is obviously their obvious scope. See, the Gulf Stream system is here, so the major attention has been paid to this part here. If you go ahead. This is another. This is an international expedition which has been done in 57, 59, which is it was the International Geophysical Year Atlantic program, and you can see the number of stations. All these dots are the stations done in 3 years, and you can see that this is the international program. So that means that there are a number of national ships participating there, and again has to be the strong assumption of the synopticity of these measurements, which has been done in 3 years, but we will assume it has to be assumed that this is the instantaneous picture what has been obtained from these measurements. And then we start with thinking of the climate. So that means we start with thinking of defining the climate overview of the world ocean. And that was the time of the world ocean circulation experiment. So what is the circulation in the world ocean? Let's try to understand from the experimental data the circulation of the world ocean. So that's why is this series of transect has been constructed. A series of large number of national ships has been involved in this huge international experiment, which gives us a lot of information on the circulation of the global ocean, not only the surface but also deep and bottom circulation in the world ocean. A large number of experimental data has been obviously connected. And here we are now in a modern era, in the era of satellites. This is the top exposure tracks in the Pacific Ocean during the 10-day repeat of the orbit. So what that means? That means that in the 10 days, the satellite produces the map of the world ocean, with this resolution. Okay, so what we used to assume that instantaneous picture of the world ocean was before 5-6 years. Now we have the assumption of a 10-day picture of the world ocean circulation, which is really a huge step ahead. The result of these measurements is the sea level, the sea level structure of the world ocean. You will see later how a number of information can be obtained from that, not only the sea level as itself, but also the circulation. When we come to the geostrophic flow, you will see that from sea level slope, we can calculate the currents. So that means not only the sea level pattern, but also the circulation pattern can be obtained from such pictures. And obviously, as you can imagine, that the problem with this kind of measurements is that they give you the pattern at the surface. We don't know what is happening in the deeper layers. So in order to obtain the information in deeper layers, we have to have ships. We cannot base all our knowledge on the satellite data, and this is the problem with satellite data. Similar to this, but different coverage is, for example, sea surface temperature measurements, the ocean color measurements, and so there are a number of parameters which can be measured from satellites, which we use in oceanographic studies. Okay, so this is how we evolve the idea, or how the possibilities of the satellite, of the oceanographic measurements has evolved with time. And in order to do oceanographic studies, we do have to do some initial assumptions. Okay, I want to study, for example, tides. If I want to study tides, I have to know something about it. I cannot study a phenomenon in the ocean without knowing anything. I have to know, for example, that the tides have the period of 12 or 24 hours. And this is the only way I can organize my measurements because without knowing anything I cannot do the measurement. So I have to design my experiment, or I have to design my measurements on my previous knowledge of the phenomena I'm going to study. And so first question I have to respond is, what is the purpose of the exploration? Do I wish to test hypothesis or describe process? If I want to test hypothesis, I have to come up with a hypothesis and then organize my measurements in a way that that this hypothesis I can confirm or not. If I want to describe the process, then I have to know simply the time and temporal and spatial scale of my phenomena I'm going to study, and then do the design of the experiment, do the measurements. The thing is, the second question is what accuracy is required for the observation. If I do the measurements on, for example, of tides, I do, for example, the measurements from satellite, I know the tides, amplitude of tides goes from several tenths of centimeters to several meters. So my precision has to be smaller than 10 centimeters, has to be on the order of centimeter. And otherwise it's useless to use these satellite on these efforts to do the measurements, and then the accuracy is smaller than what I do. And the third one is what resolution in time and space scale is required. If my phenomena is a small scale phenomena, I don't know, like 20 kilometers, I know that my gyres or whatever are 20 kilometers, I have to do my measurements in order to resolve this eddy or this phenomena. So that means that my measurement has to be at least an order of magnitude larger than the scale of my phenomena. I don't know, if you have a 20 kilometers, you have to have at least the resolution of the order of 1 kilometer. Otherwise, you will lose all the information, all the necessary information about that. The duration of the measurements. The duration of the measurement has to be such that you are able to cover the entire, the evolution of the entire phenomena. The simplest example again for this are tides. If you are going to study tides, which you know that they are amplitude of 12 or 24 hours, you cannot do the measurements of 3 hours because you won't get anything. You just get something which you say, okay, I got a trend of the sea level. It's not a trend. It makes part of the cycle which takes like 12 or 24 hours. Therefore, my measurements of tides has to be long as many cycles of tides. Otherwise, I will not, because then on the other hand, you know that tides are not variable only on 12 or 24 hours, they are variable only on the 15-day period, so that you have to be, your measurement has to be enough long to cover the whole periodicity which appears and which is associated with tides. So these are essential questions if you want to design the observational experiment. So it's essential that you know something about your phenomena, what you are going to study. You cannot start from the scratch and then study the phenomena. We mentioned before accuracy, but then there is a precision. Accuracy is the difference between the measured value and the true value. This is the accuracy. Okay. While the precision is the difference among repeated measurements. So these two things are essential in organizing in choosing the proper instrument, the proper measurement technique, in order to get the accuracy and precision good enough to give you the information on the phenomena you are going to study. Let's go ahead. Okay, so now if you have any question, you just ask. But this is like a pretty trivial thing, so I don't give you no questions. Even if you have questions, you just ask, you interrupt me. And just few information on the physical settings of the Earth ocean. This is, for example, a histogram on the depth of the world ocean. So the frequency of different depth in the world ocean in kilometers, and this is the height of the land above the sea level. What is the essential difference between these two? Is the distribution of the depth of the world ocean is like a normal type of distribution, and the average depth of the world ocean is like almost 5 kilometers. So the world ocean has the average depth around 5 kilometers, and you see how very small percentage of the world ocean is very shallow. The largest part of the world ocean is 5 kilometers. The height has quite a different distribution, and you have most of the land has height above the sea level close to first 100, 200 meters. So this is just to give you an idea. How the distribution of the world ocean looks like. From here you can see that the world ocean is really very deep. It's 5 kilometers deep, the average ocean. So what we see, or what we are in contact with in our recreative activities, swimming, tourism, fishing, navigation, we are in contact with the first few hundred meters of the ocean. The largest part of the world ocean is really something where we are not very much in contact, although it doesn't mean that we do not influence the rest of the ocean. We do influence the rest of the ocean a lot by pollution, by drilling and so forth. So it's not that these deepest parts of the oceans are unsafe from our activities. Our activity really are very acting in a very important manner to this deep part of the ocean. Here are the different geomorphologic patterns of the world ocean, and you can see that the relatively shallow part of the world ocean is called shelf, where there is a strong influence of tides, high and low tides. Then there is the continental slope, where we have the large slope of the continent. Then you have the basin interior, and then you have mid-ocean ridge, which are the kind of mountains which run meridionally along our ocean. You will see later that this is the kind of a general feature of the world ocean. Then we have a seamount, which are the isolated mountains on the ocean floor. We have the trenches. The trenches are extremely deep parts of the world ocean. We know that the Philippine trench is like 11 kilometers. Then we have the island arcs. So these are the main world ocean features, ocean bottom features. And in function of that, we have also the different kind of sediments, because the currents, which are the ocean currents, which are over that area, are more or less strong, and then determine the type of the sediments which are there. Our geologists, they will explain to us later during the exam what are the differences. Okay, so this is how the ocean principal features, geomorphologic features of the world ocean. Here are the exact definition of these different features, where you see the basins are deep depressions of the seafloor, or more or less circular or oval form. You know, this is the pretty. These definitions are pretty well presented in the world ocean, even though it looks like strong generalizations. Canyons are relatively narrow, deep furrow with steep slopes cutting across the continental shelf, which are really something which is left from all the rivers. Continental shelves are zones adjacent to a continent, which are extending from the continent to the open sea, and they are up to 200 meters deep. Continental slopes are the areas where you have a strong slope. Plains are the flat surfaces in many deep ocean basins. Ridges are the narrow elevation along of the seafloor with steep sides and rough topography, like mountains, like mountain chain. Then seamounts, like isolated mountains. Sills are the low parts of ridges separating the ocean basin, so you will see that the semi-enclosed part of the ocean are separated by the ocean by the sill. And then trenches, as we said, are long, narrow, and deep depressions. So, here it is how it looks like. A cross section at the bottom of the Atlantic Ocean. Look at these. Look at these two. This is the same picture, but presented separately, but presented in a different way. One different way. This is the first cross-section of the South Atlantic along 25 south, showing the continental shelf onshore of South America. Then you have a seamount, which is this is the real. This is what we were talking before as generalization. Here is the real pattern or real structure of the world ocean depth. And then you have a seamount, and you finally have another side of the cross. Here is the South America, and the other side is the South Africa. And you can see this is another seamount, the other seamount there. And here is the same graph, but what are the differences between the two? This one is, this upper part is the vertical exaggeration 180 to 1. What that means? That means that we have exaggerated the vertical scale 180 times with respect to that horizontal. Why we did that? We did that because if we didn't do that, we would see the line, because the ocean, the ratio between the vertical dimension of the ocean, which is on the order of 1,000 of a kilometer, with respect to the horizontal scale of the ocean, which is on the order of 10,000 kilometers or even more, it would be like a line. So in order to see something, we had to exaggerate this vertical scale and see what is this. And from now on, we'll be always looking at the vertically exaggerated scale. Otherwise, you won't see anything in our graphs. And even if we exaggerate 30 times the vertical scale, you see that we do not see anything. So take into consideration all the time when you see the graph of the whatever is in the ocean, that we are always exaggerated like 180 times the vertical scale with respect to the horizontal scale, by the simple reason that the ocean is much larger than the deep and deeper. Okay, so let's This is something what is another interesting application of the satellite altimetry, or the measurements of the satellite from measurement of the sea level from the satellite. What we see here? We are looking now at the sea surface, but looking at the sea surface, what we really see the bottom topography, the bathymetry, and the yellowish part are the shallowest part. The bluish part is the deepest part. And if you, for example, let's concentrate to the Atlantic Ocean, where, see, this is the Atlantic Ocean, right? You recognize this? And you can see that there is more or less meridional extension of this relatively shallow part. And this relatively shallow part is this central meridional mountain chain which appears, which we were talking in the generalized way of the ocean. You can see that some sea amounts, isolated sea amounts. You can see in the reddish along the continents. You can see the very shallow part, which are the continental shelves, and so you can see the whole series of these features. Which, so obviously the ocean bottom is not flat, but it's very rich in structures. The Pacific Ocean has a much smoother bottom structure. The Indian Ocean also shows the similar feature as the Atlantic Ocean, and you can see the large areas of the shelf. Shelf areas in some areas, you can see that the Mediterranean, which is here, is much extent, to largest extent, the shelf area. How do we get this from satellite, from the sea level measurements? So let's go back for one. Okay. So, from the satellite we measure the sea level, and the level surface corresponding to the sea surface of the ocean. So the sea surface at rest is a special surface which is called geoid. Okay, to first approximation, geoid is an ellipsoid that corresponds to the surface of a rotating homogeneous fluid on a solid body rotation. So that means that this fluid is rotating together with the earth which is below. So solid body rotation, which means that any single particles in the water moves together with the earth below. And if to a certain approximation, the geoid differs from the ellipsoid because the local variations in gravity. Because the local variations in gravity means that the Earth is below is not completely homogeneous and it's not perfectly ellipsoid. It has these seamounts and it has different deformation at the bottom. So in each point, the gravity is perpendicular to the sea surface. Okay. The thing is very simple when the sea floor is horizontal, because the sea surface is horizontal because the gravity is perpendicular to that. So you have the part where the sea floor is horizontal, the sea surface is horizontal as well. If you come to the area where the sea floor has a deformation in it, the deformation in the sea surface is also appearing because the gravity is perpendicular to the deformation, and then has to be perpendicular also to the sea surface. So the sea surface deforms in order to follow this deformation in in the gravity vectors. And therefore, any deformation in the seafloor can be seen in the sea surface. Obviously, if you have the seamount, which is 1,000 meters high, the deformation of the sea surface will not be 1,000 meters, because the sea surface has to be more or less horizontal. We will have the deformation on the order of a centimeter. For the deformations of the seafloor on the order of kilometer. But anyhow, since we have the precision of the sea level measurements on the order of a centimeter, we are able to measure and to determine the formation of the sea floor in the ocean. And this is how we get, from the measurements of the sea level, how we get this map here. This map shows exactly what is the form of the bottom. And this form of the bottom is obtained from the sea level measurements because of the property what I just explained to you. Okay. So this is another, I would say, another application of the bottom measurements. You can see, for example, the zoomed measurements on sea level measurements on the Atlantic, which is the Florida, North America. This is the entrance to the Mediterranean. This is Spain here. This is Africa. This is South America here. And you can see this feature at the bottom of the Atlantic Ocean. You can see number of sea mounts. You see how many of them are here? And you can see that these are also the different structures, like the wavy structures, which are perpendicular to these features. You can see the large shelf area, which is this reddish area here, along the North American coast, along the Southern American coast, African coast. So narrower is the shelf, the deeper, the closer is the continental slope to the coast, to the land. We can what's that? Okay. This is another example again, even more. This is the continental shelf over the western coast of California coast. This is the Monterey, and here you can see again obtained from satellite, and you can see that you can see these canyon. These are the canyon at the bottom of the ocean, which crosses they are like rivers. They're crossing the continental shelf, and they are like very deep canyons, which appear also at the land, but here appears in a deeper part. Okay, this is another example. How do we see with very high resolution images the bottom pictures? Let me skip over this one for a moment. Okay. So we have now made a short introduction on methodology, on general principles of measurements, of the history of the measurements, in order to give you an idea what is on the scope of the, yes?
Excuse me, Professor. How important are these principles when it comes to inland lakes?
How important are these?
The principles that you are applying to the ocean when it comes to the inland lakes.
when they come in
When we compare them to the inland lakes.
inland lakes, the same. Inland lakes, when you study inland lakes, is the same thing, except that you are doing with a smaller scale. Inland lakes are the order of 10 kilometers and so forth, and say 10 to 100 kilometers, not more than that. And the phenomena are obviously a little bit on a smaller scale, but this time you have to take into consideration your horizontal scale, your horizontal resolution has to be smaller. You don't do anymore with the kilometer. You can maybe go down to you can go up with higher resolution on the order of 100 meters, for example. So, for example, if you look at the influence of the wind, in the case of the small lakes, you have to take into consideration the rotation of the Earth, because rotation comes into becomes important on the large water bodies. If you do the studies on the relatively small water bodies on the order of 10 kilometers, you can forget about for example, the Earth rotation. So you have to adapt your measurements to this kind of, to the presence of different physical phenomena. As a matter of fact, the first one of the important measurements which are then extend to the oceanography are started from Switzerland lakes. So they did some measurements, some studies, which then has been applied to the world ocean. On the big lakes on Northern America, there are huge literature of studies there, which to a certain extent are different from the studies of oceanographic studies, but the principles are those. You have to take into consideration the time and space resolution of the phenomena you're looking for. You have to take into consideration the precision and accuracy of the instruments you're approaching. You have to know whether the rotation, for example, is important or not, and this kind of stuff. Earth rotation. Okay? So essentially it's the same thing. But whenever you want, you can ask me, and I can give you some adaptation to whatever I was talking to what you are interested in. Okay. Other questions? Okay, no question. Now we are going to heat balance. Heat balance in the world ocean, as I mentioned before, has to be zero. Has to be zero by a simple reason that the ocean temperature cannot go up or down. And so the sum of the obtained, absorbed heat and lost heat has to be zero. So in order to get this zero, we have to know what are possible sources and sinks of the heat in the world ocean. Sinks in terms, what I am saying is sinks of the heat for the world ocean. I mean the processes by which the ocean loses heat, and sources are the processes by which the ocean gains heat. So let's go numbering these phenomena here and try to describe it. One is insolation, which is the flux of sunlight into the sea. So this is the only source of the heat, the only important source of the heat for the world ocean. And so whatever is coming into the ocean, which is number one, has to be balanced by these four remaining processes. So the first process is net infrared radiation, net flux of infrared radiation from the sea. That means that the ocean radiates the energy which is proportional to its temperature, like a black body radiation. And by this, the ocean loses heat. The warmer is the ocean, the higher, the larger amount of heat it loses. There is a exact law which connects the heat, the radiation of heat, and the temperature, which you know probably, the Boltzmann. And why is this important for our studies? This is important for our studies because this property, that the ocean radiates the heat proportional to its temperature, is used in the measurements of the sea surface temperature from satellites. Because the satellites are really measuring the black body radiation, transform this into the temperature, and then from there we obtain the sea surface temperature distribution over the entire ocean. This is very, very important application to this first influx losses, red infrared radiation net flux from the sea surface. Okay. Obviously, the story is not so simple because in the mean you have the absorption of this radiated heat by the atmosphere. You have the influence of the clouds, the humidity of the atmosphere, and so forth. So there are a number of corrections you have to be used in order to get the right number, the right value of the temperature at the sea surface. Then the second process of the sea surface heat loss, or the heat loss, is a sensible heat flux. Sensible heat flux is the heat loss from the ocean, which is simply due to the difference of the temperature between ocean and atmosphere, which are in a direct contact. Which can be also, to a certain extent, can be also positive, obviously. Because if the ocean is colder than the atmosphere, then the ocean gains heat from the... But this part is relatively small. This term is relatively small with respect to the net infrared radiation. And with respect to this number 4, which is a latent heat flux, which is associated to the evaporation from the sea surface. Latent heat flux is loss of heat due to the evaporation from the sea surface, because every time during all the time the ocean loses the water due to the evaporation, but losing the water loses also the heat, because parts of this heat which is accumulated in it is lost to generate the evaporation. So this is the latent heat flux. And finally, which is this one, which is not a typical like these three one, is advection of heat, which is carried out by currents. Here we don't have the exchange of heat between the ocean and the atmosphere, but we have the exchange of heat within the ocean. So the heat within the ocean is redistributed by currents, by water movements. Why so? Because, as I mentioned before very shortly, the ocean gains much less heat in the polar areas than in the equator. If there were no ocean currents, if there were no movements in the ocean, the differences in the heat content and in the temperature, because the temperature is a measure of the heat in the ocean, the differences in temperature between these two parts of the ocean will be larger and larger. So you will have, finally it will explode, these differences in temperature between the polar and equatorial areas. But thanks to the ocean currents, which are trying to keep these differences constant, there is a continuous flow of currents from the equator toward the polar areas, and at the same time the continuous flow of the heat from the equatorial areas to the polar areas, which then, to a certain measure, tries to keep these differences constant. So the difference between polar areas in the surface of the ocean and the equatorial areas of the surface of the ocean is of the order of 15-20 centimeters. But this 15-20 centimeters remains such. It doesn't change in an appreciable way, thanks to this advection term. Okay? So, finally, conservation of heat requires that the Q total is solar, latent, sensible, no, so the long wave. This is the long wave, latent, sensible, and advective term. This has to be 0. Obviously, if we do this, we do in order to get the total heat balance, we keep these 4, and this has to be 0. This QV as internal term, it doesn't enter into the total balance of the heat. So QT, total heat flux, excluding this one, has to be 0. These 4 terms has to be 0. So if this is a positive term because this is the C surface, this is the heat gain. These 3 are the heat loss. So this is QS minus these 3 terms is equal to 0. Okay, so this is very simple expression for the heat balance. And now the question is what about the climate change? In the case of climate change, this balance should not function because we have, for example, a heating of the world ocean. So this term, in the case of the climate change, is not anymore 0. It's different than 0 because there is a long-term accumulation of heat in the world ocean because of the various processes which I don't want to enter into details right now, but this balance is not anymore 0. Obviously, this is almost 0. It's really a very small number, but this small number helps, if I may say, helps the increase of the global temperature of the world ocean. Okay. So this is the conservation of heat. Okay, so let's see a few the diagram just to you see when the distribution of this total heat. This is the total heat. Its distribution with the wavelength is not homogeneous. It has a large amount of heat. We have around some wavelength, like around 0.5, 0.6 micrometer, and this is generally the distribution, black body radiation which comes from the sun, and this is something which really comes at the top of the atmosphere, this continuous line. You see that how the black body radiation at 5,900 Kelvin is very similar to the solar radiation of this thing. So the sun radiates as a black body at the 5,900 Kelvin. Or similar to that. You can see that these two curves are very similar. So this is when it comes to the top of the atmosphere. When the solar radiation comes to the surface of the sea, it reduces its total energy. Obviously reduces because the atmosphere absorbs parts of this energy, and it also it absorbs a different wavelength differently, and this is what comes into the touches in a certain way, or is absorbed by the ocean. This thing, this curve here. Okay. The major part of the energy which comes from the sun is, from the point of view of energy, is the part which is the infrared. Okay, so heat. So the ocean absorbs this infrared, and it absorbs very quickly. It absorbs in a very thin surface layer, on the order of centimeter. Practically the whole infrared energy coming from sun is not coming from sun, coming from the atmosphere, which passes through the atmosphere. Already first centimeter of the ocean absorbs most of this energy. So, but as I mentioned before, this first centimeter is not the one which is extremely hot, and then below it's very cold. No, this first centimeter is very efficiently mixed by the wind influence. So you do have a very even distribution of this heat, which is absorbed in the first centimeter, in a layer which is on the order of even 100 meters. So the vertical mixing due to the wind is extremely important in redistributing this surface absorbed infrared energy from the sun. Okay, so let's see what offers us the next slide. Oh, this is not. Okay, this is a very complicated graph. What I just told you in words. You see that this is incoming solar radiation, which is this number here. Part of it is reflected by aerosol and atmosphere, reflected back into the space. Part of it is reflected from the surface, and like half of this is absorbed by the surface. Okay, and that's when we measure the temperature from the satellite. This thing complicates very much our estimates of the temperature, because of the sea surface temperature, because we don't see, because the sea, once it is warm, it goes has a long wave radiation, which is this number here, which goes back into the space. But part of it is absorbed by the atmosphere, and part of it goes into the space. And this part of going into the space is something what we measure in order to get the sea surface temperature. But we lost all the information which is absorbed by the atmosphere. So we have to introduce a rather heavy correction when we calculate the sea surface temperature measured from satellite. Here we can see there are greenhouse gases. Greenhouse gases, you've already heard as this term when we talk about the climate change, because greenhouse gases are those which are absorbing this surface radiation goes up into the space, and it's absorbed partially by the greenhouse gases. These greenhouse gases then, once they absorb this energy which is radiated from the sea surface, they give back this energy, radiate this energy back to the troposphere. And they contribute, these greenhouse gases contribute that our troposphere is warmer than it would be without them. So the Earth is, thanks to greenhouse gases, is much more friendly environment thanks to greenhouse gases, because average temperature of the world atmosphere is like a 15 degrees. It would be like on the order less than zero if there were no greenhouse gases. So greenhouse gases is something which are present naturally in the atmosphere. The problem with humanity, is that we are producing extra quantity of greenhouse gases, which are then increasing this term here. They are increasing the back radiation from these greenhouse gases, and they are continuously increasing the temperature of the atmosphere. So we are not really producing from the scratch these greenhouse gases. They are already there, but we are increasing the amount of greenhouse gases, and this is why we have this increase of temperature. Here is also the latent heat due to evapotranspiration and so forth, and that's it. Okay, this complicated diagram is essentially very simple. Okay. Here's interesting diagram. With this diagram, I think we should finish. This diagram shows the zonal average of heat transfer to the ocean by insolation. So zonal average means that we are doing the average from one pole to the other pole over the entire Earth. And this is these different heat flux component. This is the solar radiation, which is the only positive component from the point of view of the ocean. Positive means I'm receiving. So and you see that this heat flux component, received heat flux component, more or less it shows the maximum around the equator, with this small inflection, which is due to the presence of the clouds. And these clouds are really decrease. It causes a small decrease on of the heat coming into the to the ocean surface. And you can see how it goes to almost zero in the polar areas. This is the south and this is north, but you can see that they are pretty symmetrical. And then we have a sensible heat flux. You can see that the smallest component. We have the LW. What is LW? Long wave radiation. You can see that this is again negative, which eliminates, which irradiates which is proportional to the temperature. And finally, we have the latent heat loss. This latent heat loss, you can see that this latent heat loss corresponds more or less to this minimum of the surface of the solar radiation, because here latent heat loss is the evaporation is very strong. Due to this strong evaporation, there is a high cloud coverage, and this cloud coverage blocks, to a certain extent, blocks the solar radiation. So you can see how these two correspond pretty much one to another. And then if you want to calculate the total heat flux, you can see the net heat flux through the sea surface calculated from the data. This is the solid line, and net heat flux constrained to give heat and fresh water transport by the ocean that match independent calculation of these transports. But let's look at this thing here. if you look at this, this thing here, you can see that there is a huge difference between the equatorial areas and the polar areas where you have heat losses. And these heat losses has to be balanced by the heat transport by the ocean currents. And okay, so I don't want to go into details of the dashed curve. And so this is essentially how it looks like. So you can see that if you do the integral over the Earth, it pretty much fits what we have been talking about with these details like influence of cloudiness around the equator in the equatorial areas and so forth. Let's see if we have one more graph or what before we. Okay. Let's look at also this thing. This what we have seen before is really what is here, but spatial distribution, 2D spatial distribution of the surface of the annual mean heat flux through the sea surface in watts per meter square. Typically, it's expressed in watts per meter square. This is the 40-year average from the World Ocean Meteorological Model. And if you look at this thing here, is the blue the blue is gain and the red is loss. I don't know why it shouldn't be opposite, but it's a question of convention. Anyhow, you can see that essentially the equatorial area is characterized by the strong heat loss. Strong heat gain. Yeah. Strong heat gain because the solar radiation is major over there. And this, but you can see that it's not characterized by the simple, it's not perfect zonally distributed areas. They have some structures in it. And you can see that there are some areas where there is no this zonality in this loss area. This is the gain, the surface heat gain along the South American coast. Along the African coast, even though it should be, according to this zonality, should be already the loss area, the heat loss area. Why is so? The difference is, and also here you can see that this loss area doesn't extend all over the ocean, but it's on the other side you have the gain area. Why is this so? This is so because of the circulation in the ocean. Because we know, later on we will talk about a lot, this area here and this area here are the upwelling areas, the areas which brings to the surface the cold water. This cold water, that means that we have a larger loss because the areas are not gaining such enough heat from the This is the larger gain because the sea surface is cold, and even though the sun is not heating as much, the gain is still very large because the sea surface is relatively cold. So it's cold because there is this upwelling. Upwelling means that the cold deep waters are reaching the surface and they're cooling the surface, and this surface becomes cool, and then the relative contribution of the solar radiation is major, even though we are in an area where the solar radiation is otherwise relatively poor. Here, for example, here, this thing here, this area here, where you have a strong heat loss, you have here strong heat loss because there is a transport of the water from here over currents along the western coast of the ocean, transport of warm water toward the equator, toward the pole, and you have a large heat losses because the relatively warm water is in an area where the sun doesn't heat enough. There is a strong heat loss. So these are this is the Gulf Stream area, and this is the Kuroshio current area. This is the Australian eastern boundary current area and so forth. So it's not the perfect zonal distribution of the heat loss or heat gain. We'll come back to this nice picture which gives us a lot of information on the both the heat gain and heat loss and the circulation in the ocean. Okay, so I will stop here, and I have to